In our last example for this section, we want to look at, again, optimizing a multivariable function, but now one that has a constraint. In example 4, a company produces 2 models of a particular product each week, X units of model A and Y units of model B, with a profit in dollars given by the following function. So far, this is very similar to what we saw in example 3, but now we have some additional information, and that's telling us that due to available labor, the company can only produce 866 units each week. So we have a constraint on this scenario. What we want to find out, though, is how many units of each type should be manufactured per week to maximize profit. In order to do this, with this additional constraint being applied, that production has a cap, we need to create a new function, which we'll call capital F of xyk, meaning we're introducing a new variable, which will be composed of f of xy. That's just the function that we're given in the problem, or whatever function we're looking to optimize, plus k, which is a new value, a new variable that we're introducing, times g of xy. And this function g of xy is constructed from the information we're given about the constraint in the problem. In this case, we're told the company can only produce 866 units each week. That means our constraint is that x plus y, however many units we're producing, is capped at 866 units. So this is our constraint statement that we'll have to factor in to this expression. And in particular, what we'll do is rewrite this as the function g of xy is equal to x plus y, and then we'll subtract or move over all the terms to the left-hand side of that equation to write this as x plus y minus 866. That is, our function, capital F, will be 33.18x squared plus 21.45y squared minus 22.91x minus 36.48y plus k times this constraint function that we just established, x plus y minus 866. As a quick side note, if you see this process referenced somewhere, lots of times they use the symbol lambda. It's a Greek letter. Greek letters just tend to throw people off a little bit, and frankly, they're just harder to type in since we have an English keyboard. So in place of lambda, we're just using this value k, but it doesn't matter either way. It just represents a new variable that we're introducing into the problem. Now that we have that function set up, we need to find 3 partial derivatives, f sub x, f sub y, and f sub k. To do that, we need this delta over delta x notation, and then we'll input our function that we just created. We'll first find that first partial derivative with respect to x. Then we can go back to what we already input. And if we click in that delta over delta x notation, we can change that to delta over delta y to find the first partial derivative with respect to y. And then we can do the same thing by changing that to k. We'll find the first partial derivative with respect to k, and record each of those results along the way. So what we ended up with here would have been 66.36 times x plus k minus 22.91, 42.9 times y plus k minus 36.48, and x plus y minus 866. We established our constraint function, g of x, y, created this new function, capital F, found all three of these first partial derivatives. The next step is to turn each of these into an equation set equal to 0, and then we need to solve this system of three equations. That would be quite a bit of work, but fortunately we can make use of Symbolab to solve each of these equations. So we'll enter that first equation, the first partial derivative with respect to x, and the first partial derivative with respect to y. And click Go to get our result. In this case, we get decimal values for x and y and an exact value for k. The nice thing is we don't really care about that value for k. We need it as part of the problem-solving process, but it doesn't factor into our practical answer or our practical interpretation of this information. So what we care about right now are those x and y values. Specifically that x is going to be 339.9033 approximately, and y will be approximately 526.0967. Those are our optimal values for x and y. Now we need our optimal value for the profit, or our optimized function value, meaning we'll evaluate the profit function at those values for x and y that we found. Note that what we're doing now is going back to that original profit function. Because what we want to do is evaluate that profit function at these optimized production levels. Or I should just say for now, these optimized values for x and y. And the result that we get is our optimized function value. So all of this work is to tell us that the maximum profit of $9,743,329.81 will be attained when the company produces 340 units of Model A and 526 units of Model B. So ultimately the same answer, but we go down a very different path, quite a bit longer path, because we have this constraint information, which leads to the construction of that constraint function, the construction of this new function, capital F, and this process that we walked through to get to that result.